The Hertzsprung-Russell diagram lab is a lab designed to introduce you to this plot. And we would be plotting stars in two different classifications. We would be plotting a collection of near stars, which are stars that are near our solar system, and a collection of stars that are the bright stars that in the night sky are most apparent. And we would plot these two collections of stars and compare how they appear on the Hertzsprung-Russell diagram. So one of the major surprises about the Hertzsprung-Russell diagram that caused people to continue to pursue what we could learn from it was that stars don't just lie anywhere on this diagram. And it's the trends that emerged on this diagram that taught us about the evolution of stars. Our lab begins with a review of the axes of the HR diagram, including how bright something appears compared to how bright something is. So when you look at the sky and you see stars of different brightness, you're perceiving their apparent brightness. And the units of apparent magnitude are introduced. And when you're talking about how bright something actually is, you're talking about absolute magnitude. And absolute magnitude and luminosity are the same quantity in different units. So our original lab gave units of absolute magnitude. So how bright stars are truly in units of magnitudes. And we're also given their spectral class. So from O, B, A, F, G, K, M, including the subclasses from O0 to O1, 2, 3, 4, 5, 6, 7, 8, 9, all the way through M9. Again, recalling that the spectral class is determined by the absorption features in the spectrum of a star, and which absorption features turn up in the spectrum of a star is fundamentally a result of the temperature of the surface of the star. So temperature is also listed here along the horizontal axis, coincident with the spectral classes that the temperatures correspond to. So for example, the sun is a G2 star. So here's G0, here's G1, here's G2, and its surface temperature is approximately 5800 Kelvin. So our original lab, we would be plotting the collection of stars that we see in two populations. Table 1 is the collection of bright stars in the sky. So that's what you would call a biased sample. It's just looking at the sky and looking for the stars that appear brightest from our random position in our galaxy here on Earth in our solar system. And this collection of stars has their spectral class listed and their absolute magnitude, and we would plot all of these stars, all 1 to 10 through 18, 19, through 37, so 37 bright stars of the night sky. We would plot with one kind of marker, such as a pencil or a pen, on our HR diagram here. So using their spectral class and the absolute magnitude, we would plot those stars. And then we would switch our pen or switch our pencil or the color of our pen. And then we would move to the next set of tables and also plot these near stars. So these near stars to Earth, in our solar system, would correspond to what's called a fair sample. It's a collection of stars that don't have any bias in them. An analogy would be if you wanted to study something about people, a bias sample would be, say, you pick just all the people who are over 6 feet tall and analyze them. But if you wanted a fair sample, you would pick people randomly. So it's not a biased sample. So the near stars collection just happens to be a chunk of space, and we have 1 all the way through 30 stars. We'd be plotting 30 additional stars that correspond to the near stars on this HR diagram. And the amazing thing is that they're not scattered any which way across this plot, and they exhibit trends. Here's a quick demonstration of the equivalency of the two different axis sets between the original lab and the one that we will be using. So our original lab included 2 tables of stars that gave absolute magnitudes for the stars and that gave spectral class of the stars from O0 to M9. And we would have plotted the 2 sets of stars with those 2 pieces of information about each star. But I just want to show you that if I switch spectral type to temperature, surface temperature of the star, not the core temperature, the surface temperature, and if I switch the absolute magnitude to the luminosity, we still have these stars in their same locations. You can talk about the HR diagram using absolute magnitude or equivalently luminosity, or you could look at stars' spectral type or equivalently their surface temperature to compare them. And we would lead through an analysis of these 2 different populations of stars led by the report section questions that begin here with 1 through 10. So instead of plotting those 2 tables of stars on our data page, we're going to use this applet, Hertzsprung-Russell Diagram Explorer, that allows us to plot those collections of stars directly. Now notice that the axis in this HR diagram is not absolute magnitude like we would have used in lab. It's luminosity, and it's luminosity in multiples of this quantity here called L sun, and that's referring to the luminosity of the sun. So these units are multiples of the sun's luminosity. So for example, 10 to the 0, that exponent is equivalent to 1. So 10 to the 0 equals 1, so 1 times the luminosity of the sun. If we have a star that has that, it would be somewhere along this horizontal axis here. And the surface temperature, let's take the sun for example, at about 5,800 Kelvin. The temperature is plotted on the horizontal axis instead of the spectral class, OB-AFGKM, but temperature is really what determines the spectral class of the star. So the surface temperature is plotted here, and here at 5,800 Kelvin and luminosity, 1 solar luminosity, you have the sun is already plotted. And here on the left, it tells you what the properties of the star are at that point on the plot. So the temperature of the surface of the sun, 5,800 Kelvin, luminosity 1 times the luminosity of the sun, and using the temperature and the luminosity, you can calculate what the size of that object must be. And so the sun is 1 solar radius. This symbol R sun or R star is the symbol for multiples of the sun's radius. So if you change these properties, this little cursor will move on the HR diagram. So for example, if I increase the temperature, you see the star moves to the left towards higher temperature, higher surface temperature. If you bring it down to have a lower surface temperature, it moves to the right. If you were to increase the luminosity of this object, it increases and moves towards the top of the plot. And if you were to decrease the luminosity, it moves towards the bottom of the plot, recalculating the radius each time. So what we would be doing with this applet instead is doing the analysis with just clicking on the near stars. So notice how this collection of near stars, each is a green dot, is not scattered everywhere all over this plot. Even though there's this tremendous range in luminosity that stars exhibit, they actually show trends. So this near set of stars, you're going to investigate what the properties are, you're going to characterize it, and then you can also look at the bright stars. So again, instead of us plotting each of these stars on this diagram and then analyzing it, we're using this applet to plot them for us. So these blue dots is the collection of bright stars in the night sky, and you can also notice down here at the bottom you can plot both of them. So the green is the nearest stars and the blue stars are the brightest stars, and that is the data set that we have for our lab. I'll just note one more thing about this interactive. The temperature on the horizontal axis and the luminosity on the vertical axis are the defaults, and I left them as the defaults to discuss the plotting of the nearest and the brightest stars, but in fact you can change the axes such that luminosity is the absolute magnitude as our original data set had, and you can change the horizontal axis to correspond to spectral type, although it does not show the subclasses that is in our original data. And you can also add some information about the luminosity classes. And so we see this swath of stars going from the lower right to the upper left. That typically is called the main sequence, but for some reason they called it dwarfs here. So just note that that's atypical to call this main sequence dwarfs